Hi and welcome everyone. In this video, I want to talk about lines in R3 or 3D, or especially equations of lines in R3. Now, let's just kind of review in XY plane. We know the equation of a line can be written as y minus y naught equals to m times x minus x naught. This is, I'm sure you're all familiar with that, the point slope formula, where m is the slope and x0 and y0 are the coordinates of a point on the line. Also, you have seen this formula y equals to mx plus b, and that's the slope-intercept form, and m is the slope and b is the y-intercept. Now we're gonna see how we can find the equations of lines in 3D or R3. In order to find the equation of a line in R3, so let's call L the line, and we can determine when, or we can find the equation when we know we have a couple of information. One is a point on the line, and you know we're in 3D, so I call that x0, y0, z0. That's on the line, and to the direction of the line L. So let's see what that one is. Little note here for you: in 3D, the direction of a line is described by a vector. So that's we know that if you have a vector, the vector has a norm or magnitude and a direction. So in order to find the equation of the line, we have to know the direction of that vector v. And let's see what they are. So I try to number them for you here. Number one, we know that well, let a point x, y, z, we don't know what x, y, z are, so that's why we call that an arbitrary point on L, and I have it here. So that's the point P. I just put x, y, z. We don't know what x, y, z are in this case. Then we have r and r naught. These are, when I, you know, this is vector notation, be the position vectors of P0 or P naught and P. So we can also write them OP, the vector OP, and the vector of OP naught, actually, for P0 and OP. So again, a position vector when goes from the origin to that point. So this is our R, as you can see, and this is our R naught. So these are the position vectors. Now, number three, if A is the vector representation of P naught, P0, so if A is this vector going from the point P naught to P, or P0 to naught, please watch the previous videos by triangle law. For vector addition, we know that this vector R can be written as R0 plus A. And what is vector v here that we were talking for? The direction vector v is just a position vector, again going parallel to the line always, and going from the origin, and it can just continue. And these are the components of that vector a, b, c. One thing we know, that the line and this vector are parallel, and this is our line L here. So now I put since A and V are parallel, that means parallel. So we know A, this vector and that vector are parallel. And two parallel vectors, we know they're scalar multiple of each other. So what we can write, we can write A as T times V. So the vector A can be written as T times V. Now, what's vector R? We said vector R is R naught plus vector A, but instead of A, we can substitute A by TV, and we can say, therefore, R can be written as R naught plus TV. So Now, what is this? This is called the vector equation of the line. T is a constant and that's a parameter. So each value of the parameter gives the position vector R at a point on L. So depending what, you can take any constant for T. Now, if the components of vector V, as you can see, if I call them A, B, C, then well, we can write the vector V as when you see this notation, this is vector notation, and that means the component. You can also write AI plus BJ plus CK. I'll show it to you very soon. So T times V can be written as T times A, T times B, and T times C. Now also, we know the components of vector R can be Rx, Y, Z. Let me go back here. So again, this is the vector R. And if I write the components of vector R, I can say the vector R is X, Y, Z. Now, if we substitute, so TV can be written as that, and we have R. So we know that, and this should be R0 or R0. The components of that vector are X0, Y0, and Z0, or X0, Y0, and Z0. Now, let's just substitute. We have the vector equation, so which is here. We said R equals to R0 plus T times V. The components of vector R are X, Y, Z. We saw that. The components of vector R0 is X0, Y0, and Z0 plus, and the components T just right there, and the components of V are A, B, C. So you can just substitute, and guess what? This is just vector addition. So if I add X0 to T times A, so I have X0 plus AT. Same for the Y component. So you have Y0 plus BT and Z0 plus CT. Now, if we separate them, we can say X equals to the X component of this vector is the X component of that vector, because the vectors are equal. So X can be written as X0 plus AT, Y can be written as Y0 plus BT, and Z can be written as Z0 plus CT. These are called the parametric equations of a line. Now we can, in all of them, all three of them, we can isolate T. So for the first one, if I isolate T here, T is X minus X0 over A. In the second one, if I isolate T, you can take Y to the other side or subtract Y from both sides and divide by B. So we get that expression. And same as here, if I isolate T, we get Z minus Z0 over C. So these are all the same thing and they equal to T. And these are called symmetric equations. So depending what the problem wants, so you can find the vector equation, the parametric equation, and the symmetric equation. And here I have the same thing, some details. So we know this is our line L, this is the vector A, I talked about it. This is V, which is parallel to A. The coordinates of point P, this is point P, is X, Y, Z, and the vector R here can be written as, so these are not equal, this is just R, can be written as, and I can fix that, we can say vector R can be written as Xi plus Yj plus Zk, just another notation. Or you can say this is just X, Y, Z. So please be careful when it's vector notation, these are components. That's how you write them. And then you have parentheses, these are just the coordinates of a point. And vector V, I just put the different notation here. The components are A, B, C, so you can write that as AI plus BJ plus CK. Now let's do some examples. Let's see how we can use those. The first example says find a vector equation. So remember here we want vector equation and parametric equation for the line that passes through the point 5, 1, and 3 and is parallel to I plus 4j minus 2k. So now one thing we know, if we work on this example, this is a point on the line. So this is just R0, the coordinates are known, so P0. And we know if I write the vector R0, it can be written as 5, 1, the components are 5, 1, and 3, or we can write that as 5i plus j plus 3k. Now the vector v is parallel to, and is parallel to that. So vector v, the line is parallel always to vector v. So vector v is I plus 4j minus 2k. Now if I write the vector equation, I can say r equals to r naught plus t times v. So we have r naught, the components of r naught, and that's plus t times, and that's our vector v. And again, you can separate the x components, y components, and the z components, or just write it like that. So it's going to be 5 plus t times I plus 1 plus 4t times j and plus 3 minus 2t times k. So in this case, we know this is our x and this is our y and this is our z. And these are the parametric equations. The question is not asking for symmetric equations as we saw here. If it was asking for that, then you can just isolate t and put them equal to each other. I think we have that in the next examples. Now another one, find the parametric and symmetric. There we go, we have it. Equations of the line that passes through, these are points. Don't forget, A and B are points. So if this is our line, we're given the coordinates of a couple of points on the line. Now what we need to do is to find that vector. So how do you find the components of that vector? You know, please watch the last videos on finding the components of a vector. So the first component is going to be 3 minus 2, and the second one is -1 minus 4, and 1 minus -3, which is 1 plus 3. So these are the components of this vector, and we know that vector is parallel to v. So we can write v as that using the components. Now the vector equation, we know it's r plus r naught plus t times v. R, the components of r are just x, y, z, and I'm going to just go back here again. We have the components of r, it's x, y, z. There are arbitrary components, so that's why we call just x, y, z, and that can be written as we have r naught, we already found out. So r naught is going to be, or you can, what you can do is just pick one point, and then we want to find any of those points are going to work. So r naught, we can take the components of the vector going from the origin to A is just 2, 4, 3, 2, 4, -3. So let me fix that also. So I picked the point A, and the R naught, I picked the component of R naught. Again, the way you find that, you can just say 2 minus 0, 4 minus 0, -3 minus 0, because it's from the origin. So you get that plus t times, and v, we already found the components of that vector, and then the x component of the vector we want to find or vectorize 2 plus t. So it's just going to be 2 plus 1 times t is t. Then we have the y component is 4 plus t times 5 is 5t. And finally, the z component is going to be -3 plus t times 4 is 4t. Now the parametric equations, again, we know x is that, which is 2 plus t. Y is that one, which is 4 plus 5t. So that's 4 plus 5t. And finally, we have the z component, which is negative 3 plus 4t. Let's do another one. Find, here is a and b. So it says find the parametric equation and symmetric equations for the line. The first one is the line through the origin and the point 4, 3, and negative 1. So these are the coordinates of a point on the line, and it passes through the origin too. So if we go directly to vector equation, we can write r equals to r0 plus tv. Now, what is v? Since the line passes through the origin, you can just directly use that, or if you want to find the component, is 4 minus 0, 3 minus 0, and negative 1 minus 0. So the components of v are 4, 3, and negative 1. Then you can write again, r is x, y, z here. Then you can pick 1 point on the line, and it doesn't matter. This line passes through the origin, so it's much easier to get the origin, which is 0, 0, and 0 plus t times v. So x, y, z can be just written as t times v, which is t times 4, negative 3, and negative 1. So you get x equals to 4t, y equals to 3t, and z equals to negative t. And also you can, what you can do is isolate t here. So here, if I isolate t, so we can say for the first one, t equals to x over 3, and that equals to, from here we get y over 3, and z divided by negative 1, which is negative z, and this is going to give us the symmetric equation, and that's not 3, this is, the first one is 4. So parametric equations and symmetric equations. The second example, the line through 2 points, that we kind of see that, but let's go ahead and work on this again. So we have 2 points on the line. So what we want to find is the components of v. We know v is parallel to the line, so if you want to find that components, we can do 3 minus negative 8, which is 3 plus 8, negative 2 minus 1 is right here, and 4 minus 4. So if you do that, you get 5, negative 3, and 0. Then you can write r, a point on the line, doesn't matter which one you pick. Here I picked the first one, so it's negative 8, 1, 4 plus t times v, and we have v here. Now I think you know what to do, so r can be written as negative 8 plus 5t, 1 minus 3t, and 4. So the x component is negative 8 plus 5t, y equals to 5 minus 3t, and z equals to 4. Here, so we can say t is isolate. T in this one is x plus 8 over 5. For the second one, you get y minus negative 1 over negative 3. For the third one, if you do that, so z minus 4 equals to over 0. We know we can't have that, so we can just write that as z. So these are the parametric equations, and these are the symmetric equations, and these numbers are called the direction numbers. I think that's good enough for this video. Please, you're ready to do the homework now. Try some examples, and in the next video, I'll go over the equations of planes in 3D. Thank you for watching, and I'll see you in the next video. Have a great one.